Hey everybody. Today I will be talking about a recent paper, Hamiltonicity of inhomogeneous random graphs. This is joint work with Frederik Garbe and Simón Piga from the Institute of Computer Science of the Czech Academy of Sciences, where I also work. And as a quick note, the reason I try to upload versions of my talks on YouTube is that I'm somewhat reluctant to travel due to environmental considerations. So at least you can see these presentations on YouTube. Okay, so let's get to what is the subject of the paper. And before diving into inhomogeneous random graphs, let me briefly recall the homogeneous Erdős-Rényi model denoted as G and P. The model uses a deterministic vertex set of size n. So n is an integer, and then further we have p, which is a real number between 0 and 1. And the meaning of it is that each pair of vertices forms an edge independently with probability p. As n grows, we typically scale p to 0 to study interesting structure changes, such as the emergence of a giant component or Hamiltonicity. And this also corresponds to our understanding of the real world. So for example, maintaining a constant expected degree as a real world network growth requires p to decrease as to scale as 1 over n. Now, I want to give you two theorems about this homogeneous case, and we will see their inhomogeneous counterparts later. So these theorems establish the threshold for AAS, so that's asymptotic almost sure connectivity and Hamiltonicity in G and P. So if P is smaller than log n over n, the Erdős-Rényi random graph asymptotically almost surely contains an isolated vertex. And on the other hand, if p is increased just slightly above this threshold, the graph becomes connected. This connectivity result dates back to the foundational papers of Gilbert and Erdős-Rényi from the late 1950s. Notably, at this exact same threshold, the graph also becomes Hamiltonian, meaning it contains this Hamiltonian cycle, so a cycle going through all the vertices. Logically, the third point, which talks about Hamiltonicity, renders the second one mathematically redundant, since any Hamiltonian graph is inherently connected. However, there is a historical gap of nearly 2 decades between these discoveries, proving Hamiltonicity is vastly more involved than proving connectivity. This latter major milestone was finally achieved by Porsche and independently by Korshunov, and both of them developed different methods, but methods which proved useful in many other settings. Now, let us introduce the inhomogeneous model, or more specifically, graphon-based random graphs, right? Because the word inhomogeneous is very general, and people may mean other random graph models by saying inhomogeneous random graphs. A graphon, here and elsewhere denoted as W, is a symmetric measurable function on the unit square, taking values in the unit interval. And by symmetric, I mean that when you swap the coordinates, the value doesn't change. And by measurable, I mean Lebesgue measurability. And if you are not too familiar with Lebesgue measurability, don't worry too much. We will use it only in some intuitive sense. The concept of graphons originates from the theory of dense graph limits that was developed by Borges, Chayes, Lovász, Sors, Szegedy, and Vesztergomby around 2 decades ago. And I like to think about this theory with a certain duality in mind. And that duality can be likened to the relation between statistics versus probability. So on the statistics side, if you will, you can study a deterministic sequence of growing dense graphs. And that's one of the main theorems of that theory, a result due to Lovász and Szegedy. Due to compactness, you can assign a limit graphon to that sequence, or at least to a subsequence of it. And on the probability side, which is what we are going to do here, you can use a fixed graphon to generate random graphs. So now I will describe how you generate this random graph G and W, where W is a graphon. Okay, so I'm using a very similar notation to the homogeneous case, but now I'm replacing the second parameter, which used to be just a real number, by a much more complicated object, a two-variable function. To generate a random graph G and W with sample and independent points uniformly from the unit interval, each sampled value acts as a vertex position. For any pair of vertices, an edge is inserted with probability given by the graphon evaluated at their respective positions. So you can see this on the picture here. I have this sample graphon. And I'm now generating G n equals 4, comma W. So that's the graph is going to be on the very right. And what I sample 4 points on the unit interval. I reflect them to both axes, which form the ground space of the graphon. And now to decide whether the edge 2, 3, for example, should be inserted, I use the position of the graphon at x2, x3. And by the way, it doesn't matter if I'm using the position x2, x3 or x3, x2. That's what this symmetricity assumption is giving me. So also, as a quick note, let me describe how I visually depict graphons in these slides. They will appear a lot. You might say that I use a somewhat non-standard orientation for the Euclidean plane. In particular, the 0, 0 corner is the top left, and the 1, 1 corner is the bottom right. While unusual for Euclidean geometry, this is perfectly standard in matrix theory. In fact, you can think of graphons as infinitesimal versions of large adjacency matrices squeezed into the unit square. And you will also notice my color coding. Y represents zeros as values, black represents the value of 1 in a graphon, and various shades of gray represent the values in between. A simple intuitive example of this is the stochastic block model. This is an example. This is the case where you can partition the ground space into a finite number of blocks, like, oh, wait. Like I'm doing here with blocks A, B, C, so that on each of the rectangles generated by these blocks, the graphon is constant. You can think of the stochastic block model as having a finite number of communities. 3 is in this example, community A being somewhat smaller than communities B and C, where friendship probabilities between any two people depend solely on which two communities they belong to. Okay, so stochastic block model is a particular case of graphons. As a rule of thumb, whenever you have a calculation for the homogeneous Erdős-Rényi case, so it can be a calculation regarding the chromatic number, the clique number, whatever you can think of, you can usually extend it to the stochastic block model with just a bit more effort. The calculations become just a bit longer to take into account these finitely many different blocks. However, the true richness of the theory of inhomogeneous random graphs and the need for deeper real analysis and measure theory emerges when we view the full graphon model as an infinite refinement of this, allowing us to work with all measurable functions. In the Erdős-Rényi model, I said that we usually study sparse regimes by scaling the probability P to 0 as n goes to infinity. That is, many questions about Erdős-Rényi random graphs are quite easy and uninteresting when P is kept constant. There are indeed inhomogeneous models that do something similar. For instance, the Bolobash-Jansson-Riordan model scales the graphon to generate sparse random graphs. So what you would be looking at are things like Gn, W over n. So n appears even in the second parameter. However, in our result with Simón and Frederik, we do not use scaling. Our fixed graphon model G and W generally produces dense graphs, that is, graphs with a quadratic number of edges in terms of n, as long as W is not constant 0. In analogy with the homogeneous case, you might think that this makes properties of G and W trivial or boring, but this is not the case. And I will try to convince you about this in this talk. That is, even though the graph is dense on average, the graphon may harbor sparse localized regions, so regions where the values of the graphon get close to 0, that fundamentally impact the global structure. And one example where you can see this is connectivity, which I already mentioned in the homogeneous case. Okay, so in the homogeneous case, I mentioned these two results. One was about connectivity and the other about Hamiltonicity. Now, what I would like to do in the rest of the talk is to go through these inhomogeneous counterparts to these two results. Okay, so we want to understand asymptotic almost sure connectivity of G and W. So in particular, let us look for reasons why G and W is asymptotically almost surely not connected. And the first obvious obstacle to connectivity is a disconnected, or sometimes also called reducible graphon. Okay, let me define that. It's a notion which appeared or is quite standard. I think it first appeared in a paper by Jansson. You say that a graphon is disconnected if the unit interval on which the graphon lives can be partitioned into two sets of positive measure. Let's call them R and B, like red and blue, with the property that the graphon is zero almost everywhere on their cross section. Okay, and now I claim that if the graphon is disconnected in this sense, so that's a graphon definition of disconnectedness, then G and W will be disconnected asymptotically almost surely. So what happens when we sample from such a disconnected graphon? Both the red and blue sets will contain a linear fraction of vertices asymptotically almost surely. Okay, so what is happening? There is this two-stage generation process. In the first stage, you just generate the vertices into the unit interval, and some of these vertices will fall into the red part, and some of the vertices will fall into the blue part. Okay, and all I'm saying is that many will fall into the red part, many will fall into the blue part. As a matter of fact, the only thing I would need is that there is at least one vertex in the red part and at least one vertex in the blue part. Because the connection probability between these two sets is zero, the resulting graph will split into two isolated linear-sized components. Thus, a disconnected graphon trivially yields a disconnected graph asymptotically almost surely. Okay, so that was one obstacle. Now, let's look at another obstacle, which I call here isolated vertices, and we will see shortly why. Okay, so what I have on the picture is a graphon. It's an example of a graphon defined by Wxy equals x to the 6 times y to the 6. So x and y are elements of the unit interval, so I can take their 6 powers, I can multiply them. Right? And you can see how that graphon looks. The values are relatively high, close to the 1,1 corner, and they are quite small along the x equals y and x equals 0 and y equals 0 axis. Now it is easy to check that the graphon is connected in the sense of the previous definition, because it doesn't have any zeros, or it has zeros only around the x-axis and y-axis, which is measure 0. So that can be discarded. Still, I claim that the resulting graph G and W, even though W is a connected graphon, will be asymptotically almost surely disconnected. And it will be disconnected because it will contain an isolated vertex. So that's a reason, it's a very different reason than in the first obstacle where there were two huge components. So now here there will be one tiny component, an isolated vertex. Okay, so let's consider how for such a graphon the vertices are generated. So again, we are throwing in these n many vertices in the unit interval. Okay. And what happens is that these vertices on the unit interval, they are reasonably equispaced. Okay. So the leftmost point will have value around 1 over n. The value of the leftmost point, let's say it's less than 1 over square root n. Okay. For this specific vertex, its maximum connection probability to any other vertex y is at most n to the minus 3. Even with n minus 1 potential neighbors, right? Every vertex has n minus 1 potential neighbors. The expected number of edges for this vertex is nearly 0. So you can do a quick calculation and conclude that such a vertex asymptotically almost surely will have 0 friends. The power of 6 was chosen somewhat arbitrarily. It is not the optimal threshold. But if you try to repeat the previous consideration for graphons of the form x to the alpha times y to the alpha, you will see that you will not succeed in arguing that there is an isolated vertex if alpha is less than 1. And as a matter of fact, below this threshold, the graph remains asymptotically almost surely connected, and above it, isolated vertices begin to emerge. Okay. So observe that x to the alpha times y to the alpha, such graphons, such a family of graphons, does contain values arbitrarily close to 0. So it's not about the presence of very small values. It's more about how many such small values there are. Okay. To quantify that, you need to introduce the notion of graphon degree. So for a given point x in the unit interval, its graphon degree is simply the one-dimensional integral of the graphon slice along y. This is a counterpart to graph degree, because indeed, if you have a graph and you want to define the degree of a vertex in an algebraic way, what you can do is you can look at the adjacency matrix. You can take the slice of the adjacency matrix, so the column corresponding to that vertex, and you can sum up the values in that slice. So here, summation was just replaced by integration. The reason why degrees are relevant is because in our generated graph G and W, a vertex assigned position x will have an expected degree roughly equal to n times its graphon degree. So there is a clear relation between graphon degrees when the vertices are assigned their position, but the finite graph hasn't been generated yet, and and graph degrees of the random graph. And now, if there are too many points with near zero graphon degrees, isolated vertices will appear. That's the intuition. Okay. So here is the theorem characterizing connectivity of G and W, which I obtained with my colleague Gopal Viswanathan. If W is connected, we define S alpha, actually we don't need W to be connected. We define S alpha to be the measure of points with graphon degree below alpha. And now, if S alpha decays faster than alpha, as alpha approaches zero, low degree vertices are rare, and G and W is connected. If S alpha decays slower, hence forming a heavy tail, the graph will contain an isolated vertex, asymptotically almost surely. There is also an intermediate regime where the limit is strictly between 0 and infinity, or where the limit limit behavior oscillates or doesn't exist. We can characterize those as well. Don't worry too much about them here. Okay. So somehow a compact way of thinking about this theorem is that there is a clear obstacle for linear sized disconnectivity, and there is another clear obstacle for isolated vertices. And these are sort of two extreme versions of disconnectivity. And in some sense, these are the only potential reasons for disconnectivity in inhomogeneous random graphs. Okay. So this theorem covers or is a counterpart to these results of Gilbert and Erdős training. Now let's look at the other half of results I promised, and this is indeed what I did with Frederik and Simón in this new preprint. That is, having fully characterized connectivity, we want to look at Hamiltonicity. In the Erdős-Rényi model, the thresholds for connectivity and Hamiltonicity are identical. So our main question is, does this equivalence hold in the inhomogeneous setting? Or does Hamiltonicity in G and W require additional conditions, additional to those we had in the previous theorem for connectivity? Well, this example shows that just the conditions for asymptotically almost sure connectivity are not enough for Hamiltonicity in the inhomogeneous model. Let me describe the graph on W shown on the left. I partition the ground space of the graphon into three parts, which we will call x0, x1/2, and x1. These names have a natural meaning that we will see shortly. And the key conditions are that W is constant 0 on the cross-section of x0 with both x0 and x1/2. So that's one condition. And the other is that the Lebesgue measure of x1 is strictly smaller than the Lebesgue measure of x0. And we don't much care what happens on the rest of the space. You can assume, for example, that W is equal to 1 on the remaining parts. So that's the maximum value. Okay, so you can easily check that this graphon satisfies the connectivity conditions of the Hladký-Viswanathan theorem, or alternatively, you could directly check that the graphon will be, that the random graph GNW will be connected asymptotically almost surely. Yet, I claim that the generated random graph GNW will not contain a Hamilton cycle asymptotically almost surely. Okay, so if I convince you of that, then we will have identified a new obstruction for Hamiltonicity. To see why, consider the two stages of generating this random graph. So in the first stage, we throw our n vertices into the unit interval, and we can think of these vertices as being assigned types based on these three sets, on the sets x0, x1/2, and x1. By the law of large numbers, the proportion of vertices in each set will mirror their measures in the graphon. Because W is 0 between x0 and x0 union x1/2, no edges will be generated in those regions. So that's the same argument as we had for the first in the first obstruction for connectivity. Consequently, the only potential neighbors for the vertices in x0 lie in x1. Okay. Since x1 is strictly smaller than x0, the graph does. So, okay, maybe I will show that before saying the argument. The graph looks like this, right? So the white regions, in particular this one and this one, they show that there are no edges in between. Okay, and then so the vertices of the x0 part, there is a bigger number of them than the vertices in the x1 part. Okay, so what I need to show now is that this graph does not contain a Hamilton cycle. As a matter of fact, I will prove a bit stronger property that it does not contain a perfect matching. Right? Perfect matching is a stronger property. And as a matter of fact, the way I will prove that is by proving an even stronger property, that it doesn't have any matching which covers x0. And this is obvious because the only partner a vertex of x0 can have in such a supposed matching would be in x1, but there are simply not enough vertices in x1 to be partners to vertices of x0. Thus, we have found a template for graphons that yield connected but not Hamiltonian random graphs. You might wonder if this is just an ad hoc construction and if there are other complicated obstructions requiring, say, 15 blocks, right? I might come with some super complicated constructions. There would be 15 types of x's, and there would be zeros forced in some parts. Actually, it turns out that this is a general template and the only obstruction. What is missing from the connectivity conditions is essentially a requirement for the existence of a perfect fractional matching. So now, as an audience who are, I guess, more familiar with random graphs and extremal graph theory, I will assume that, or I will go a bit slower about this sort of LP duality and combinatorial optimization business that is involved. So you can recall the standard LP duality, that is, the maximum size of a fractional matching is is captured by its dual, the minimum weight of a fractional vertex cover. Okay, so when I said that the problem, the obstruction here is in G, the additional obstruction compared to connectivity is in G and W not having a perfect fractional matching, which is obviously a necessary condition for Hamiltonicity. We would like to transfer that condition to what it means for the graph on W, which serves as the base of the model. And as a matter of fact, I wrote papers about sort of matching theory for graphons previously with Ping Hu and Diana Piguet and Martin Dolezal. And one of the messages of those papers is that actually there is no nice concept of matchings for graphons. Yet, there is an elegant dual theory, so the dual theory of fractional vertex covers for graphons, and this perspective can save us. So the specific partition we just saw translates precisely to the graphon lacking a half integral vertex cover of total weight less than 1/2. Okay, so by the way, there is a quick calculation which I have shown here. These two inequalities are equivalent, and the green inequality is really very close to saying, well, if the sets x0, x1/2, and x1 represent some measurable counterpart to fractional vertex cover, then the total weight of this vertex cover is less than 1/2. We will discuss the specific details of half integrality and fractional covers of graphons in later slide. So I will skim over them now. For now, just keep in mind that the finite world obstruction to a perfect fractional matching, a fractional matching which is too small, which has average less than 1/2, translates perfectly to this specific partition condition to the graphon setting, or in the graphon setting. This brings us to the main theorem obtained with Frederik and Simón. Just a warning, the version I'm presenting here is slightly imprecise. There is a minor condition missing here that I will address on the very last slide. But in this imprecise version, the theorem states that G and W is asymptotically almost surely Hamiltonian if and only if it satisfies these three conditions. The first two of them we saw in the theorem with Gopal Viswanathan. That is, the graphon is connected and the low degree vertices have a light tail. And the third one, we saw it on the previous slide, is that there is no partition of the unit interval into x0, x1/2, and x1, satisfying the zero cross-section condition and the relation between their size, or alternatively, their weighted average being less than 1/2, which we just discussed. And let me just say that such a structure x0, x1 half, x1, we call it a peninsula, and I think you can see the graphical similarity here. So let us proceed to the proof of the Hamiltonicity theorem. We have already established the negative direction, showing the disconnectedness, heavy tails of low degree vertices and peninsulas are undeniable obstructions. Now we must prove the positive direction. Assuming these necessary conditions are met, we want to prove that the random graph G and W is asymptotically almost surely Hamiltonian. So in our approach, as the most basic tool, uses Wuchak's so-called connected matching method, which is applied together with Semeredis regularity lemma. Okay, so I will assume some sort of familiarity with Semeredis regularity lemma, and I will very briefly explain Wuchak's connected matching method. So we are given our graph G and W, and we apply the Semeredi regularity lemma to it. This partitions the vertices of the graph into a bounded number of clusters, and obviously the key feature of this partition is that we have edges in this auxiliary graph between almost all pair of clusters that behave quasi-randomly, and these are called regular pairs. They come with different edge densities, which I represent by different shade of gray. The cluster graph essentially acts as a finite approximation or bounded approximation of our original graph on W, inheriting its structural properties. A major part of the overall proof is understanding how we can utilize these inherited properties from the graphon to the structure graph, to the cluster graph, to guarantee the specific structural features we need in the cluster graph, which, as we will soon see, turn out to be matching properties. I will detail exactly how we achieve that translation from the continuous graphon to the discrete cluster graph later in the talk. For now, let's focus on why matching properties are so useful. So matching properties in the cluster graph. Okay. And so why are we, let me just recall why we regularize graphs in many applications in extremal graph theory, is that we have these tools like the blow-up lemma. And using these tools, we know that a regular pair with positive density behaves nicely enough to contain an almost spanning path. Okay, so the blow-up lemma essentially tells you that, the blow-up lemma of Komlos, Sarkozy, and Semeredi, but actually it may be an overkill, and this particular property you can prove. There is a 5-line proof of that when you are trying to embed just a path. Okay, so now we can explain Wuchak's connected method argument. The strategy is to find a perfect matching in the reduced cluster graph. And if we can find such a perfect matching, and if we can connect the edges of this matching together, we can lift this structure back to find an almost spanning cycle in the original graph. Okay, so we would apply the blow-up lemma to each of the regular pairs, but not of all pairs, but only those that are present in the perfect matching. And that would, what that would give you is a system of paths which covers almost all the vertices of the original graph. And you do need to do some additional ad hoc work to connect these paths into a Hamilton cycle. So this is usually tedious, but somehow the idea is it should work. But for the bulk of the argument, we need to understand whether we can find a perfect matching in the cluster graph. And I was lucky on the picture I have here. On this picture, I managed to find a perfect matching. But can I do that always? Well, it turns out, unfortunately, that I don't have such an argument. But we will relax the problem. Because a perfect matching in the cluster graph, what does it mean? I'm just sort of doing now basics of combinatorial optimization. A perfect matching in the cluster graph would just mean assigning an integer 0 or 1 to every edge in such a way that the sum of the weights of the edges incident to any clusters is exactly 1. Okay? And I don't have an argument that this always happens. But there is this well-known approach of relaxation. So we relax the problem. And instead of demanding a perfect integer matching, we look for a perfect fractional matching. So we allow the edges to take on continuous weights in the interval 0, 1, such that for every vertex, the sum of the weights of its incident edges is exactly 1. But here is the crucial part. We do not actually have to deal with arbitrary real numbers. So many of you are familiar with the fact that in a bipartite graph, the existence of a fractional perfect matching automatically guarantees a true integral one. While odd cycles, for example, show you that you don't get this integrality property in general graphs. A fundamental property of the matching polytope, known as the half integrality property, ensures that we do not lose everything. In a very real structural sense, every graph retains exactly half of that bipartite integrality. Okay, so that is, if any perfect fractional matching exists, there is guaranteed to be a half integral one. So one can safely restrict our edge weights to just 0, 1/2, or 1. This is the first time we rely on so-called half integrality property. And we will see another application where we use it on the dual problem, on the problem of vertex covers later. Okay, so if a perfect fractional matching exists, we have that there also exists a half integral one. So we update our goal. Instead of searching for an integer perfect matching, we look for a perfect half integral matching in the cluster graph. And now, if I can find arguments which guarantee at least that one, at least a half integral one, how can we utilize that? If we can find it, we can connect, we still can use it to build our almost spanning cycle. So why? Well, how does a half-integral matching actually look? In a half-integral perfect matching, every cluster has a fractional degree of exactly 1. That means that cluster is either linked to exactly one other cluster by edge weight of 1, or it's linked to exactly 2 other clusters by edges of weight 1/2. In the case of an edge weight of 1, we use the regular pair as it is. So I think I have one example here. I'm using the blow-up lemma to find an almost spanning path in that as is. In the case where a cluster has 2 edges of weight 1/2 linked to it, so there are many examples like that, for example, this one, we simply subdivide that cluster into 2 equal halves, assigning 1/2 to one neighbor and the other half to the other neighbor. And the beautiful thing about Semeredis regularity is that it is robust. A significantly large subpair of a regular pair is still regular and maintains roughly the same density. Because of this, these subdivided halves still give us regular pairs we need to apply tools like the blow-up lemma and lift our paths. So now the question is, can we guarantee this perfect half-integral matching to exist in our cluster graph to begin with? And this is where LP duality comes in. We must relate the existence of a fractional matching to fractional vertex covers. Sorry, let me just erase these. A fractional vertex cover of a graph assigns a weight from 0 to 1 to each vertex such that for every edge, the sum of the weights of its endpoints is at least 1. Note that every graph trivial has a fractional vertex cover if we just assign the constant value of 1/2 to every vertex. Okay, so the challenge is in producing cheap, light fractional vertex covers. In particular, you are asking whether you can beat the barrier of 1/2. And now we have the core LP duality argument, where we rely on the half integrality property for the second time, this time on the dual side. By strong LP duality, if our graph does not contain a perfect fractional matching, it must contain a fractional vertex cover with an average vertex weight strictly less than 1/2. Just as with the matchings, we cannot necessarily find an integer vertex cover that is small. However, the polyhedral structure guarantees that we can always find a half-integral one. Therefore, the exact dual obstruction to our matching is the existence of half-integral vertex cover, assigning only weights 0, 1/2, and 1 to the vertices that has an average weight strictly less than 1/2. Well, let's define a half-integral vertex cover more precisely. If you have a function assigning weights of 0, 1/2, and 1 to the vertices, then you can partition the vertices into 3 sets based on their weights, x0, x1/2, and x1. For this to be a valid vertex cover, there can be no edges between x0 and x0, nor between x0 and x1/2. Because if there were, the sum of the weights on that edge would be less than 1/2, sorry. So by LP duality, if our cluster graph lacks a perfect half-integral matching, it must have one of these covers where the average weight is less than 1/2. Okay, so we are at this picture, and I think this picture is a familiar one. Okay, so we are trying to deal with this unfortunate situation when Wuchak's connected matching argument fails. So we cannot find a perfect half-integral matching in the cluster graph. By the LP duality, this failure implies the existence of a half-integral vertex cover in the cluster graph with an average weight strictly less than 1/2. Okay, and we want to find a contradiction specifically to show that this implies our original graph on W had a peninsula, which was forbidden in the conditions of the theorem. To do this, we need a way to relate structures in finite graphs to structures in the continuous graphon. So we use the method of weak star limits. To introduce the method of weak star limits, let's look at a simpler toy example. Okay, so we want to use properties of weak star limits to relate half-integral vertex covers of cluster graphs to those of a graphon, and I want to be working with independent sets instead of vertex covers. Okay, and I will be following a paper I wrote with Israel Rocha some years back. So let's start with a natural definition, because I said we will be dealing with independent sets in graphons. I need to define what an independent set in graphon is. We all know what it is in a finite graph, but the definition is quite natural. An independent set in a graphon is a measurable subset X of the unit interval such that W is constant 0 almost everywhere on X cross X. And now in finite graphs, you have the notion of an independent set, and you typically are looking at the one which has maximum cardinality, and that defines the independence number. Okay, so likewise here, we define the independence number of W as the supremum of the measures of all such independent sets. Okay, so in finite graph theory, you don't usually say supremum, you say maximum, because you are dealing with a finite system of sets. Right? Here we are doing analysis, so things are not finite, and it's appropriate to use the word supremum. But the question is the supremum actually attained? Does there exist an independent set whose measure is exactly alpha W? And the answer is yes. And I want to use this as a toy example to show you the power of this, or the approach using these weak star limits. So instead of talking about sets, it turns out to be useful to talk about their indicator sets. Okay, so from now on, an independent set will be just a function which is the indicator function of the genuine independent set. Okay, and then the original condition translates into the condition where you are integrating on the entire unit square, but you have these terms that involve the indicator. Okay, so we switch to this functional notation, if you will, because that's where That's the world of these weak star limits. Now I want to explain weak star limits first in general. So not the parts not related to graphon. So this is a classical and foundational concept in functional analysis, going back to the early 20th century work of people like Stefan Banach. So it's quite possible that you have seen it in your studies, but I think it is helpful to recall it. And as a motivating example to introducing these weak star limits, let's consider this sequence. You might call it Rademacher functions. These are functions that are notoriously problematic because they oscillate between 0 and 1. So these are functions defined on the unit interval, taking values 0 and 1, but they oscillate between these two values more and more rapidly. So if you try to apply any familiar limit concept, pointwise convergence, uniform convergence, convergence in LP spaces, you will fail to produce a limit to this sequence of functions. So here is where the weak star topology comes to the rescue. Okay. If you integrate these highly oscillating functions over any measurable set, the integral smoothly approaches half the measure of that set. Because, okay, on any measurable set, if you are far enough in your sequence, half of this oscillating part is in the value 1, and half of it is in the value 0. So 1/2 on average. Thus, in the weak star topology, this problematic sequence successfully converges to the constant 1/2 function. Okay, so that was a definition by example. So now here is a proper definition. Formally, a sequence of functions Fn from 0, 1 to 0, 1 converges in weak star to a limit function capital F if for every measurable A, the limit of the integrals of Fn over A equals to the integral of capital F over A. A key tool from functional analysis called the Banach-Aloglu theorem tells us that the space of functions from 0, 1 to 0, 1 is sequentially, it's compact in the weak star topology. This means that every sequence has a subsequence which is weak star convergent. Okay, we will be using this Banach-Aloglu theorem. Okay, so returning to our toy example, we want to prove that an independent set of maximum size exists. So what do? We take a sequence of independent sets represented by indicator functions Fn, such that their measures converge to the supremum, which is alpha of W. Okay, and now, so these independent sets, quote unquote, they are represented in this functional setting. And by Banach-Aloglu, this sequence has a weak star limit, or at least a weak star accumulation point, which we call capital F. Note that F takes values in the interval 0, 1, not just the values 0 and 1. Okay, that can happen. We had it in the example of Rademacher functions, where each function would only take values 0 and 1, but somehow we got this additional value of 1/2 in the weak star limit. Okay, so we got this weak star limit capital F, and what properties did it as a limit inherit from the functions Fn? Well, we have this one, and if you recall the definition of weak star convergence, I can take any measurable set A. In particular, I can take A to be the entire interval. So we have equality of the limit of these integrals and this integral. Okay. And what we also had is that each of the fn's satisfied this independent set condition. And now it's maybe not entirely obvious, but you can do a little calculation and infer that this condition also got inherited to the limit. Okay. So that's quite good because that condition was essential for independent sets. Nothing happened on this slide. I just moved some of the text a bit higher, since we will need 1 or 2 more lines of calculation. So where are we now in the proof? We have produced a limit function f, which has these 2 crucial properties we expect from an independent set of size alpha. However, f is not quite an independent set because it also takes these intermediate values. Independent sets only take values 0 and 1. This one takes also this intermediate values. So to fix this, we round f up. We define a new function g that is 1 wherever f is strictly greater than 0 and 0 otherwise. Because f took positive values, G will be an independent set. And since G is greater or equal to f everywhere, the integral of G over the unit interval is at least alpha of W. We do know that it can't be strictly greater than that, so it must be equal to alpha of W. Okay, so now what we do have is G is an independent set. So the support of G is indeed an independent set. The main takeaway from this toy example is that the weak star limit of independent sets after rounding up gives us a valid independent set. But now we are going to introduce a crucial strengthening. Suppose we have a sequence of graphons, Wn, that converges to a limit graphon W in the cut norm. You do not need to know the precise definition of the cut norm metric for this talk. It is perfectly fine to treat it as a black box today. But there is this absolutely central notion of the cut norm metric in graph limit theory. Okay, so now let's look at the strengthening, which is on the slide. The strengthening states that if we have a sequence of independent sets, Fn for a graphon Wn, okay, the rounded up weak star limits of these Fn's will be an independent set in the limit graphon W. Okay, so this limit graphon is in the sense of the cut norm topology. Okay, and this strengthening follows just by doing all the calculations we did previously a bit more carefully. And of course, using some properties of the cut norm at some point. I ask you to carefully keep this specific strengthening in mind, as we will need a very similar step when we transition back to half the integral vertex covers in just a moment. Okay, so that's what we are doing now. We can apply this exact same method to half integral vertex covers. Note that half integral vertex covers are in spirit quite similar to independent sets, just slightly more complicated. the core similarity is that both structures fundamentally force the graph on W to be zero on certain specific regions. The condition for an independent set is that W must be zero on the square of that independent set. A half-integral vertex cover, on the other hand, partitions the space into x0, x1 half, and x1, and similarly forces W to be zero on specific cross sections, namely x0 cross x0 and x0 cross x1 half. Because both concepts boil down to the zero region constraints, we can run the exact same analytic machinery. And the main difference is that instead of tracking a single indicator function, we are now dealing with a triple of sets. Consequently, we simply apply the Banach-Aloglu theorem on the product space to extract, so a cube of a space to extract simultaneous weak star limit of three independent sets, of three sets. After extracting this joint accumulation, we use a careful rounding procedure to obtain a valid half integral vertex cover in the limit graph form. Okay, so the takeaway here is that the properties of half integral vertex covers are lower semi-continuous. You don't get full continuity, not very important to us, with respect to the cut norm metric. This is exactly where I need you to recall the crucial strengthening involving the cut distance that I emphasized a moment ago. It is precisely this robust property that allows us to cleanly bridge the discrete and the continuous if a sequence of approximating graphs, like our cluster graphs, has a small integral vertex cover, the limit graphon is forced to inherit this property and have a small integral vertex cover as well. Now we can piece together the entire proof strategy. Step one, we assume our graph on W has no peninsula. Now we essentially go backwards through the arguments we just built to complete the proof. So let us look at step 4. Okay, if we assume that the cluster graph, so the regularization R, had a half integral vertex cover of average less than 1/2, this would translate into a peninsula in the continuous graphon representation of R. So now the question is, how does R relate back to our original graph on W? This is exactly where we apply the cut norm twice. First, there is a standard sampling theorem which tells us that the random graph G and W is close to W in the cut norm metric with high probability. Second, Semeredis regularity lemma also guarantees that when you regularize something, you don't deviate too much in the cut norm metric. So by the triangle inequality, R is therefore close to W. And by the way, I'm using slide cheating because I'm talking about cut norm distance between finite graphs like G and W or this regularization R and graphon, but this is standard. You can do that. You can work in such a metric, if you will. Okay, so we have the triangle inequality R is close to W in the cut norm metric. Because of the lower semi-continuity we established, if R had a small vertex cover, the limit graph on W would have a peninsula. But in step 1, we explicitly assumed that W had no peninsula. Therefore, R cannot have such a cover. So that allows us to move to step 3, because R lacks this small half integral vertex cover. Standard LP duality guarantees that the regularization, that this R must contain an almost perfect half integral matching. And finally, using Uchak's connected matching argument, blow-up lemma, we can pull this structure back to find a collection of disjoint paths that almost perfectly cover the vertices. The final step is to upgrade this almost perfect cover by paths into a true Hamilton cycle. So we must deal with low degree vertices, and we need to connect our paths. There are techniques involving absorbers that are technical, require many ad hoc arguments, but are reasonably standard. So again, this finishes the sketch of the proof. And what I want to emphasize, what I consider the main trick, and definitely the trick I focused on in this presentation, was to be able to transfer between matching properties in graphons and finite graphs that are close to that. And we did that using vertex covers and weak star limits. Okay, so this completes the broad stroke of our main theorem. G and W is asymptotically almost surely Hamiltonian if and only if W is connected, has a light tail of vertices, and contains no peninsula. That's the imprecise version, remember. And now let me state the precise version. The precise condition for the peninsula obstruction is that the 1/2 measure of x½ plus the measure of x1 must be less than or equal to 1/2, and the measure of x1/2 must be strictly less than 1. Okay, so let me just explain this, what it means. If you had a partition that satisfied the previous definition, where there was a strict inequality in this part, then this partition also fulfills these new conditions. Why? Well, obviously you replaced a strict inequality by a non-strict one, so this part checks. And also, if you had a strict inequality, then that means that you couldn't have the measure of x1 being equal to everything. Okay, so this part checks as well. On the other hand, there are graphons which do not contain a peninsula with respect to the previous definition, but they do have a peninsula with respect to the new definition. Okay, so this new definition does allow fractional vertex covers of weight 1/2, and we do know that every graphon does have a fractional vertex cover of value 1/2, namely the constant 1/2 fractional vertex cover. But this particular fractional vertex cover is forbidden by this condition. Okay, so the new way of thinking about it is, yes, of course, I know that my graphon does have a fractional vertex cover of value 1/2, but does it have a non-trivial one? Does it have something which is not constant 1/2 value, right? And sort of an example of such a graphon okay, it's a wrong picture, but anyway, so is the complete balanced bipartite graphon. Okay, so the values of black and white are swapped here. And so let me explain why. So this graphon, the complete balanced bipartite graphon, does possess a peninsula in terms of this new definition, because you can put this one into the first blob into set x1 and the second blob into the set x0. Okay, and now let me try to argue why G and W is asymptotically almost surely not Hamiltonian. So when you generate G and W, like I'm doing here, you will end up with approximately balanced complete bipartite graph. Okay, and the complete balanced bipartite graph does have a Hamiltonian cycle, so there seems to be no problem here. But actually, what you will have is it will not be perfectly balanced. It will be almost or approximately balanced, but there will be these Gaussian fluctuations because you are throwing in these points into these two bins, into these two sets at random, so it will not end up exactly in half and half. There will be slight fluctuations. And these fluctuations will mean that, that you will not have a Hamilton cycle. Okay, and with that, let me finish the presentation. Thanks.